Hey everyone, welcome to chapter 13. So, this chapter is all about gravitation, right? The universal law of gravitation. So, in this video, I'm going to try and give a brief overview of what gravity really is, right? Um, Hopefully, though, before now, you should have seen the couple videos on the conceptual part of Newton's shell method, right, and where that comes from. If you haven't, please pause this video, go back, watch those, and come back here. All right. So, in the mid 1600s, Isaac Newton devised his universal law of gravitation, right, and he came up with the force of gravity, which we now know has the form of the following: the gravitational constant g times the mass of object 1 times the mass of object 2 divided by the distance between those two objects squared. And since this is a force, it's a vector, right? It has a magnitude right there, and then it has a direction, okay? So I specify that direction with an r hat. And for example, say we have two objects, right? Mass 1 and mass 2. This r hat direction is the line connecting the centers of masses. Okay, that's the r hat direction. So, for example, the force of gravity on mass 1 due to mass 2. It's right there, right? We write that force on 1 due to mass 2. Okay, that's a vector, and that points from mass 1 towards mass 2. Why? Because gravity is always an attractive force, right? So mass 1 is being attracted towards mass 2. Okay. Mass 2, on the other hand, is being attracted towards mass 1, this direction, with an equal but opposite magnitude force. So we write this, the force on 2 due to mass 1. That's also a vector. Okay. So like before, when you choose the positive directions, the plus r hat direction is really arbitrary. Okay, in most problems you'll just be dealing with Earth or just with one particle. So if you're doing problems with mass 1, say r hat is, well, that way, right? The r hat direction really is arbitrary. Okay. Now let's take a look at kind of the form of this force equation, right? The force of gravity is proportional directly to the masses of two objects. And they can be whatever mass, right? It doesn't matter. So the more mass that one object has, the stronger the gravitational force between them. I'll say that again. If somehow the mass for mass 2 kept on increasing and increasing and increasing, well, that means that not only does the force on mass 1 from 2 gets bigger, but the force on 2 due to mass 1 also increases. Okay, so that's not a very intuitive or immediate realization. Okay, the force depends on both masses directly. Next, it's inversely proportional to the distance between them squared. So, for example, these two are separated by some distance r. Right, I'll write it as r12. So if you increase the distance between two objects, well, the force decreases, but not at a linear rate, at an inverse squared rate. Okay, so what's this inverse square effect? I believe this is really the first time in the course we've talked about an inverse square relationship. So let me briefly explain that. So take an object, right, of some mass, whatever mass it is. So this gravitational force really acts in what's known as a field, right? This is a type of field. Mass right there. And by field, well, because it's a force, you can call it a force field. So what does a force field mean? Well, in essence, it means that at any point in space, right, in the volume of space around some massive object, there exists a magnitude of force at that location. And in the case of gravity, it's always an attractive force, right, towards the mass in question, towards the mass that's generating the field. Okay? There doesn't have to be a mass out here, right, in space, in the volume of space around some mass. There doesn't have to be an object out here to feel the force for there to be an actual force present at that spot. Okay? They're just, if you were to place a mass there, it would feel a force, okay, at all points in the volume around some mass. Okay, so that's kind of what a field means. Now, the inverse square, let me kind of draw something like this. Okay, so, for example, if an object was 1 meter away, right? 1 meter away from some mass m, the inverse square relationship will say that it feels some force F, right? We're going to compare that to 2 and 3 meters away in a moment. It might be best to correlate this with, say, a light source, if you will. So how about this? Inverse square law works for light as well. Actually, why am I doing blue? Let's do a light bulb. Okay? It's shining light out in all directions. Okay? The inverse square law means that the light that's passing through the square here, that's 1 meter away, is the same as the amount of light that's passing through the same that's passing through a square twice as far away. All right? So now, this square here is twice as far away as this square here. However, the total amount of light passing through this entire square is the same as the amount of light passing through this smaller square. Okay? And I can go one step further, and I can even give dimensions to these squares. Right? Say this is, I don't know, length times width. This is area A. Okay? If I'm twice as far away, this square has 4 times that area. So now, this area A is just equal to one of those 4 squares. However, if you add up the light passing through all 4 of these squares of area A, that's, again, the same amount of light that's passing through just one square of area 1A. We can take this even further and go 3 times as far away. And now, can you see what's going to happen? If I'm drawing it to scale, what should happen is that this square now, that's 3 times as far away as the first one I drew, has an area that's 9 times greater than this initial square, right? But in the third one, just one of these squares, in theory, should be the same size as this square here, okay? So that means that the total amount of light passing through this entire 9 square, right, is the same amount of light that's passing through this 4 square, and this 1 square. That was a weird sentence. All right? So this is, in essence, conserving the amount of light. But the important part, and relating this back to gravity, is that the intensity of light, or the brightness, if you will, from this square to this square, just this one, to just this one, is decreasing. So the further away from a light source you get, the the brightness of one of these squares gets dimmer and dimmer and dimmer, right? It gets dimmer by how much? Well, by 1 over 1, right? That's 1. And then 1 over 2 squared, I should square that. 1 over 2 squared is 1/4. So the intensity or brightness of just one of these squares is 1/4 as bright as this square is. When we go 3 times as far away, it's 1 over 3 squared, or 1/9. So one of these squares here is 1/9 as bright as this original one is. Translating that back to gravity, if this were not a light bulb anymore, but now an actual massive object, the analogy would be the force of gravity, or the strength of gravity. If it's, say, 1 meter away, it would be the strength F. If it would be twice as far away, the force here would be 1/4 that of what it was here. 3 times as far away, it would be 1/9 as strong as it was right here. Okay, so this is the inverse square law. The force decreases or drops off as 1 over the distance squared. Okay, and so again, it doesn't just have to happen, say, to the right, of course. It happens in all radial directions, any directions, everywhere in space, because the force is a field, right? It's a type of field. With that, thanks for watching.